Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Honest Geometry class. Today we're going to be talking about proving triangle similarity. We already learned yesterday that similarity occurs when you have the same shape with different sizes, but the corresponding angles are congruent, and the corresponding sides are proportional. Okay? Today we're going to prove similarity. Now, I don't want you to get confused. You're going to see some theorems and postulates here that repeat from congruency theorems. Don't get them confused, okay? So I'll make sure I'll do the best that I can do. Okay, so the AAA postulate. The AAA postulate states that if all three corresponding angles of a triangle are congruent, then the triangles are similar. Okay? If all of the three corresponding angles of a triangle are congruent, then the triangles are similar. So for example, if I give you these two triangles, you see the corresponding markings. The corresponding angles are congruent. Then yes, I promise you that they will be similar. Okay? That is called the AAA postulate. Now, based off of the AAA postulate, you also have what's called the AA postulate. And the AA postulate, or the AA theorem, states that if two corresponding angles are congruent, then the triangles are similar. Why in this case? Do you guys remember the no choice theorem? Very good. So if I tell you that angle A is congruent to angle D and they're corresponding, and angle B is congruent to angle E and it's corresponding, then that means that angle C has to be congruent to angle F because of the no choice theorem. Therefore, you have three corresponding angles that are congruent. Therefore, it goes back to the AAA theorem. So, AAA theorem, if all three corresponding angles are congruent in a triangle, the triangles are similar. The AA theorem, if two corresponding angles are congruent in a triangle, then the triangles are similar. Okay, these are similarity postulates. Now the next one we're going to learn is the triple S, side, side, side. Now, some of you may say, whoa, wait a second, Mr. Morrow. SSS, that's a congruency postulate. That's a congruency theorem. Yes, it is. But this is tweaked a little bit, okay? The triple S, or the side, side, side congruency postulate, states that if corresponding signs are congruent, then the triangles are congruent. The side, side, side theorem for similarity states it a little bit differently. It states that if the ratios of the corresponding sides are proportional, proportional being the key word here, they have the same ratio, they have the same proportion, then the triangles are similar. So very different, actually, than side, side, side congruency theorem. If the ratios of corresponding sides are proportional, then the triangles are similar. Okay? This is side, side, side similarity. For example, here I have triangle ABC and I have triangle DEF. AB corresponds to DE. That's 3 to 12. 3 to 12 is 1/4. So AB to DE would be a 1 to 4 ratio. AC corresponds to DF, and that's 5 to 20. 5 to 20, that's a 1 to 4 ratio. And BC corresponds to EF. That's 4 to 16, which is also a 1:4 ratio. So the corresponding sides are all proportional. That means that the ratio of each corresponding side is congruent. They're equal. So when the corresponding sides are proportional, you can use side, side, side similarity theorem. Notice that it's similarity. If on a proof one day you see side, 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 that means that they're talking about congruency. If you see side, side, side similarity theorem, you know they're talking about similar. Okay? I want to make sure you guys can differentiate between the two because it is a huge, huge difference. Okay? Now, just in case anyone is behind, I'll just, well, that didn't work. Okay. I'll just pop this down a little bit. Oh, I got to do it all again. It's all right. Okay, just in case. All right. So, I want to solve for x here. The only way I can solve for x here, though, I kind of messed up here, I just realized. I have to tell you that both of these bad boys are similar. So if I tell you that triangle, yes? Very, very good. Wow, look at the big brains on my boys. Good job. They were just, my class just astonished me. That's why I love them so much. They just said, Mr. Moore, you know that this is similar because of angle, angle. And you know what? They are absolutely right. So I don't have to say that this is similar anymore because of angle, angle. Very good, my brother. So we know that they're similar. I want to solve for x. Well, remember, we did this yesterday. Since they're similar, the corresponding sides must all be proportional. So I'm going to go ahead and say, okay, 8 to 10 must equal 9.6 to x. Because AB corresponds to DE and BC corresponds to EF. Okay? When I go ahead and cross multiply, I get 8x equals 96. Divide by 8. X would equal 12. Boom. So, again, you guys are awesome. I don't have to tell you anymore that they're similar. You can prove that they're similar. In this case, you proved it with angle, angle. Okay? So I have AAA similarity theorem. I have AA similarity theorem. I have side, side, side similarity theorem. I also have side, angle, side similarity theorem. Before, for SAS congruency theorem, if I have two corresponding sides that are congruent with an angle that's in between those corresponding sides that are congruent, also congruent, then the triangles are congruent. Here, it states two corresponding sides are proportional and the angles between them are congruent, then the triangles are similar. Okay? You want me to expand this page already? You got the first page? Yeah? Okay. Make your life easier to see. Thank you. So basically here, can I prove that ABC and DEF are similar? Yes, I can. Okay. I have here 12 to 20. Does 12 to 20 equal 3 to 5? Absolutely it does. I can cross multiply. 5 times 12 is 60. 20 times 3 is 60. Or I can reduce 12 twentieths, divide both by 4, and I'll get 3/5. So I know that the sides here, the corresponding sides are proportional, and I can see that angle A is congruent to angle D. So boom, I can prove now the triangle ABC is similar to triangle DEF. And that is called the side-angle-side similarity theorem. different than just regular side angle side. Please be careful. When you're proving this, you must put SAS similarity. You have to put the similarity symbol, please. If not, I have to deduct points. Okay? That makes sense, boys. So in a way, this is kind of cool because it's using facts that we already learned before, but we're putting it in a similarity context. Okay, that's it, by the way. You have side, 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 similarity. Side, angle, side, similarity. You have angle, angle, and you have triple angle. Okay? Make sense? Okay. That's how you prove similarity. Angle, angle, side, no. You're not going to have that. HL, no. You're not going to have that. And no, you're not going to have angle side side because that doesn't even exist as a congruency theorem. But thank you, you're very funny. Okay, I've got here that ABCD is a parallelogram. All right, I want to prove that triangle BFE and is similar to triangle CFD. So as always, I put my little figure down here. And number one, like always, we know how to do proofs. ABCD is a parallelogram. That's given. That's awesome. Remember, by saying that ABCD is a parallelogram, remember opposite sides are congruent. Opposite sides are congruent and parallel. Okay, you got to remember all those things. Remember diagonals bisect each other. All of those things are really, really important. Number two, so I just gave you part of it. AB is parallel to DC. That's a definition of a parallelogram, man. Opposite sides are congruent and parallel. Okay? If that's the case here, what do you think? What do you think can happen? If I have that DC is parallel to AB, what do you think I can get from here? Remember what I'm trying to prove here, guys. I'm trying to prove that this guy and this guy are similar. What do you think I can prove here? Awesome. Angle E is congruent to angle CDF. Okay? Look at it. This guy is congruent to this guy. Right? You see that? Why? Remember the Z method, guys? Alternate interior angles are congruent? Yes, sir. Oh, okay, yeah. What's up, Baba? Now what? Which F? There's a lot of F's. Uh-huh. Excellent, my brother. Angle DFC and angle EFB are congruent because of... I love it. Vertical angles are congruent. You guys are on fire. Please notice, though, I'm going to go back in a second. You can't just say angle D is congruent to angle E. I can call angle E because there's only one angle E there. But angle D, I have CDF, I have CDA, I have ADE. So you have to articulate which angle we're talking about. And now, since I have two angles that are congruent, I can prove that triangle BFE is congruent to triangle CFD because of, I'm sorry, my bad, Mr. Morrow. Let's try that again properly. Triangle BFE is similar to triangle CFD, thank you, brothers, because of angle. Sir.
Also, if you have gone the other route and said that
No, proving that angle A will be congruent to what? Okay, but how would angle A and angle B help you? This triangle here is not in question. The triangles in question here, my brother, are this guy and this little guy. So what you would have said, that would have been a good fact, but I probably would have put on the quiz or test, I would have said, okay, and that wouldn't have taken us to where we need to go. Sir, Phenomenal question. Wouldn't you never have to use angle, angle, angle? Yes, you would never have to use angle, angle, angle. Unless it's one of these, gift proofs that you see that the angles are all congruent right off the bat, and it could be a two-stepper where you put the given and then, hey, wait a second, angle, angle, angle. Thank you very much. Good thinking, sir. Does that make sense, my brothers? All right. This is a tasty proof. This is a good one. Okay. All right. So I've got LP is perpendicular to EA. I've got that N is the midpoint of angle P. I got P and R trisect segment EA. I want to prove that triangle PEN is similar to PAL. Okay? So again, I'm trying to prove that triangle PEN here in blue is congruent to triangle PAL here in red. As always, I'm going to start with my given. LP is congruent to EA. God, what is wrong with me? LP is perpendicular to EA. Maybe I should learn how to read. Sorry, guys. No excuses. So if LP is perpendicular to EA, what are we going to know? I couldn't have said it better than that, man. Phenomenal. I've got LPE and LPA are right angles. That's exactly 100% accurate. Well done. Then what? Very good, my brother. That's definition of perpendicular lines. So that means LPE is congruent to LPA because right angle congruency theorem. Very good. Or right angles are congruent. You cannot say right angle theorem because that's not the right one. Right angle congruency theorem or right angles are congruent. So I know that these two bad boys here, I'll just do this in green. They're both right angles. Fantabulous. Okay. Then another given. Very good. Wow, you're on fire, brother. N is the midpoint of P. So if N is the midpoint of angle P, whoa. Hold on. Did I say that? Did I write that down correctly? Did I write that down correctly? I do not think so. Ah, wow. What an epic fail. What an epic fail. Yeah, this is bad. Okay. No, we're not going to record. Sorry, Mr. Morrow's human too. N is the midpoint of LP. How can it be the midpoint of an angle? Sorry about that. So if N is the midpoint of LP, what does that tell you about LN and NP? So that's given. So LN is congruent to PN. Definition of midpoint. So I know that this is congruent to that. Okay. Then P and R trisect EA. So P, which is this guy, and R, which is this guy, trisect EA. That's a given. So if they trisect EA, what can I say? I love it, guys. EP is congruent to PR, which is congruent to RA. Fantastic definition of segment trisector. So this guy is congruent to that guy, which is congruent to that guy. Now here's where it gets a little funky. Okay? Here's where it gets a little funky. If you think about this, good job, by the way. I heard you say it, but I want to explain it. Do you see how this blue guy has one green tick mark? But LP here has two green tick marks? And do you see here how EP has two green tick marks? But PA has two green tick marks? You see that? So basically what I have here is a proportionality. LP to NP equals PA to PE, which is a 2-to-1 ratio. Does that make sense, guys? If it doesn't, let me put some numbers. Let's say that's a 3 and that's a 3, and let's say that's a 4, then that's a 4 and that's a 4. wouldn't NP to LP be 6 to 3, which is 2 to 1, right? And isn't PA to PE 8 to 4, which is also 2 to 1? Do you see that a little bit more clearly now with the numbers? So that would just be a definition of a proportion. Yes, sir.
Does the math get any more complicated than that?
No. This proportion math, no, it's about as complicated as it's going to get. Again, I made up those numbers. What I saw is I said, okay, wait a second. LP has 2 green tick marks when NP only has 1 green tick mark. So LP to NP is 2 to 1. 2 to 1. You feel me? And then I said, okay, PA has 2 double green tick marks, right? But EP only has 1 double green tick mark. Isn't that also a 2 to 1? Do you see me, guys? Now, if you don't see that, you could just attach random numbers like I did. And hopefully that really accentuates it for you. So then, how can I prove that triangle pen is similar to triangle PAL? Side angle side, similarity. Got to put the similarity here. Does that make sense, boys? That's of the harder types of proofs here. That was cake, right? It's because you're a boss, man. You're a boss. Okay? Let's do another one. Okay. KH is the altitude to hypotenuse GJ of right triangle GHJ. Okay, I want to prove that KHJ is similar to HGJ. So I want to prove that KHJ, this blue guy, is similar to HGJ, the whole entire triangle. That's what we're trying to prove, that similarity. So first of all, KH is an altitude to hypotenuse GJ of right triangle GHJ. That's given. But what is it saying here? If KH is an altitude to GJ of right triangle GHJ, doesn't that mean that GHJ, that means that that's a right triangle, right? And an altitude here, I'm going to form a couple 90s here, right? Does that make sense? So I know that HKJ, bless you, HKJ, which is right here, is a right angle. Yes, sir. No, because K is a straight angle. There's 3 different Ks. HKG is a right angle. HKJ is a right angle, but GKJ is a straight angle, 180 degrees. Could you have put both? Sure. No worries, because definition of altitude. Okay? Then from here, I can also prove what I just wrote down as well. GHG is a right angle. Why? Because the hypotenuse is always opposite of the right angle. I know that JHG is a right triangle, but which is the right angle? The one that is opposite the hypotenuse. So now think about what we have here. So that means that HKJ is congruent to GHJHG, because right angles are congruent. So basically I'm saying that this guy is congruent to this guy. And I know that J is congruent to J because of reflexive. This is congruent to itself. And therefore, how can I prove the And there is no congruency theorem here. There's a similarity theorem, Papa. Right angle congruency theorem. Right angle congruency theorem states that right angles are congruent. If you say right angle theorem, that means that if two angles are supplementary and congruent, then they are right angles. That is not what we're stating here. Here we stated that this is a right angle and this is a right angle. So HKJ and JHG are right angles. That means that JKH is congruent to JHG. We can also prove that angle J here, since it's a matching angle for both triangles, is congruent because of reflexive property. Then I can state that triangle KHJ is similar to HGJ because of angle-angle. I see some of your faces a little bit off there. That's why I'm here. Talk to me. You know I'm here for you. Yes, sir. Okay. Look, don't I have this triangle here? That's one angle, that's one angle. Then don't I have this larger triangle? That's one angle, that's one angle. Okay? What if I erase this? I am talking about JKH. And I know that this is a right angle, and this is going to be congruent to itself. And then I'm talking about HJG. Isn't this a right angle? And isn't J part of that larger triangle as well? Angle, angle. No, thank you. Does that make sense, boys? I think there's one more, right? Okay, I will take care of that right now. Just leave the class as quietly as possible. I have another class coming in. I'll wrap up this video and post it. Thank you. Have a wonderful day. God bless you. Okay, and last but not least, the sides of one triangle are 8, 14, 12, and the sides of another triangle are 18, 21, 12. Prove that the triangles are similar. Okay, let's see. Let's go smallest to smallest. Then let's go middle value to middle value. And then let's go largest to largest. 12 to, so hold on, I messed this up. Let's go small. What did I do here? Let's go small to small. So 8 to 12. Let's go middle to middle. 14 to 18. And let's go, oh my God, I'm messing this up all over the place. Let's pay attention, Mr. Morrow. Okay. Let's do this the right way. Small is 8 and small is 12. Okay, so small to small. Then middle is 12 to middle 18. And then large 14 to large 21. Okay, now we got it. So when I divide this, okay, I can divide this by 4. So giving me 3/4. I can divide this by, or I'm sorry, 2/3. Wow. I can divide this by 6, giving me 2/3. And I could divide this by 7, giving me 2/3. So even though I fumbled through this, hopefully we learned something to pay attention, learn from my mistakes. 2/3 equals 2/3, 2/3. So small, medium, and large, all of the sides are proportional. And that means that through side similarity theorem, they are similar. Thank you very much. Hope you learned a lot. Have a great day. Bye-bye.